like the CHEM. What? Crap. It's no graphic yet.
A lot of
It's toughest to make.
Straight 24-hour drive.
Say, like, I don't know, like, worth it? Probably not.
yeah, no, probably not.
It was used to find something.
Actually, so that's an important state.
All the Californians there, dude.
Yeah.
So any of these recorded lectures, 1 to 5 to 7 conversations beforehand.
Yes.
And lab. Wow, so hello Brooklyn. I had one with Iowa today. Yeah, I've actually had 12, so.
Really?
Watch this thing. I always sit here in my classes and I'm always the loudest voice. I need it.
Good afternoon, everyone. Welcome to class. Let's go ahead and get started. I would like to start with prayer. Can I invite someone to volunteer?
Okay.
Thank you.
Our dear Heavenly Father, we're grateful to all be able to visit together this afternoon and to be able to be here to learn about biochemistry and to learn about glycolysis. We're grateful for thy gospel and also for the opportunity to learn this good science. We say these things gratefully in the name of Jesus Christ. Amen.
Amen. Thank you very much. So today's the last day to take the exam in the testing center, so please plan accordingly. We are losing some people, at least temporarily, from class, so I hope they recover quickly and get back with us. Last time we had talked, talked about calculations of delta G prime zero. These are thermodynamic terms. These are ways in which we calculate the energetics of a reaction. And we will continue that conversation. We had talked about oxidations and reductions. We had talked about ways to identify biological oxidations and reductions. By far and away the most common, the simplest way to identify these reactions is the involvement of NAD+, NADH. Those are the oxidized and reduced versions of nicotinamide dinucleotide, or the FAD, FADH2. These are the oxidized and reduced versions of the flavoadenine dinucleotide, and these are the common electron recipients or donors for the majority of biological oxidations and reductions. So we'll just put that out there. We didn't do a calculation of one of these, and I'm going to do that at the beginning of the class prior to moving on to talk about glycolysis. So let me, I have written some of this out already, just in the interest of time. So let me begin here. This delta E prime zero is a constant for a given set of, given pair of half reactions, one for the oxidation of a compound, the other for the reduction of another compound. And and we're going to consider a reaction in which pyruvate is converted into lactate. This occurs when our bodies are under anaerobic conditions, or at least tissues within our bodies are not getting adequate amounts of oxygen and undergo this sort of anaerobic type of metabolism in which pyruvate is converted into lactate. What I've listed here are what you would see in the table as shown in the book in chapter 13. These are standard reduction potentials as listed. These are versus a hydrogen electrode. You need not remember that, but that's where these numbers have come from. What you can see here is both of these are negative. So as reductions, neither of them is energetically favorable. So unlike delta G, where a negative number indicates a release of energy, a tendency to go spontaneously, in the case of delta E or delta E prime 0, it's a positive number that indicates energetic favorability. And that can be seen here. So delta G prime 0 and delta E prime 0 are interrelated by this equation. This factor here is the Faraday constant, sometimes shown as a kind of a backward F or a fancy F. Its value is shown here on the board, but it should be available in the book as well. So delta G prime 0 and delta E prime 0 are interrelated by the number of electrons being transferred times the Faraday constant times the delta E prime 0. But notice there is a negative sign out in front here. So positive values here become negative values there. This delta G prime 0, if you'll recall, is a constant, and it is determined under standardized conditions, whereas this delta G represents actual physiologic or cellular conditions for a reaction. This equation is similar to the one for delta G. You'll recall that we had a delta G prime 0 plus RT, natural log of the ratio of products over reactants. In this case, it's a little more complicated because, again, we have N, the number of electrons being transferred in this redox reaction. We have the Faraday constant as well. You'll notice that in the case of this particular writing of this equation, this is negative because I've placed products over reactants. If you were to invert this, then this would be a positive sign. But I personally like having products over reactants. It keeps that ratio sort of consistent in my mind, and so I prefer to have the negative sign out here. All right, so this is sort of some background for being able to do a problem. So one of these now needs to be reversed. We need to change the direction of the reaction to represent an oxidation. Remember that if there is a reduction, there must also be an oxidation for any redox reaction. So one might ask, well, how do I know which one to change? Which one do I write differently? And the simple answer for the exam is that we will know the direction in which the biochemistry is taking place. We will know how the reaction is being used in the cell, and consequently, we will know which species is being reduced and which oxidized as part of that particular biological step. So as I mentioned, under anaerobic conditions, pyruvate is converted to lactate. Consequently, this would have to be written differently such that we start with NADH and it undergoes oxidation to produce NAD+. This is required if we're going to have pyruvate oxidized to lactate. Now notice, let me move this up here a little ways. I'm going to reverse this such that it now reflects an oxidation. So this is going to lose a hydride, and that is 2 electrons. And what I'm going to do now is I'm going to change the sign on this number. When I write it in the reverse direction, then this sign will change. So we start with standard reduction potentials, but any of them could be converted into a standard oxidation potential by reversing the direction of the reaction and changing the sign here. Yes?
What are the units there? What's that?
Oh, these are volts. Yeah, as redox reactions then. So I'm going to simply put this out. Now, I can combine these provided that the number of electrons cancel out. So here we have 2 electrons, here we have 2 electrons. So if I sum these 2 reactions, I end up with these canceling out. I have 1 of these, 2 here, so I'll cancel 1 out there. So let me rewrite this. Pyruvate plus NADH goes now to, sorry. Need to include the NADH plus that 1 proton. Go now to produce lactate and NAD+. And now I simply combine these 2 together. So let me make sure that I'm getting this correct. So this ends up being now a plus 0.135 volts.
Dr. Graves, the sound just went out. I'm not sure if it's your microphone. Yeah, I still don't hear anything. Did you try changing the source microphone? There we go. Yeah, that's, oh, it just cut out again.
Hello?
Yeah, there we go. Perfect.
Practically. All right, so I apologize to the listening audience. I was just sort of wrapping up here. On the exam, you would be given 2 standard reduction half reactions. You would need to reverse one of those to represent an oxidation that would happen in conjunction with your reduction step. That would be determined by biology in our case. So you would anticipate getting information about how the reaction was proceeding in the cell. And we know, or because that under anaerobic conditions, pyruvate is converted into lactate. Hence, I've reversed the other half reaction to represent an oxidation. NAD going to NAD plus 2 electrons. Once I've reversed this reaction, I need to change the sign for this because it's no longer a standard reduction potential, but represents a standard oxidation potential. Provided I have the same number of electrons transferred, I can simply sum the 2. If for some reason the number of electrons in one half reaction is 1, and in the other 2, I would need to multiply the terms in the equation by 2, but not the voltage. The voltage is a constant. Every electron that leaves or is gained happens with the same energy. So that this does not change, although the sign would change if I move it to a standard oxidation potential. Then I simply sum this. This gives me a net voltage for the reaction. This is the delta E prime 0. This feeds into this equation. All of these constants would be provided on the exam. All of these concentrations would likewise be given you, and it would be your task to set up the equation correctly and then solve it on your calculator. So this is likely to show up on your exam, but any questions about this? Yes?
What was the end value again?
It's the number of electrons transferred in the reaction. And so if one half reaction is 2 and one 1, you will need to multiply the 1 by 2. So in the end, you're transferring 2 electrons as part of the reaction. Yeah. Yes?
Can you repeat your explanation of why you don't multiply the E prime 0?
Yeah, and very simply, the energy to remove or the energy gained by loss of electrons remains constant.
And that's then like the change in voltage per electron or per
No,
electron
per
pair?
mole.
Per mole.
Yeah.
Oh, okay.
Okay, so so this value or this value is a constant for that given half reaction. When we multiply through, we're simply balancing electrons. It doesn't change the energetics of the reaction. Just so. Other questions? Anything from? Okay. All right, we are going to move to chapter 14. And we're going to talk about glycolysis. Oops. Is that okay? All right. So we have been working, we're trying to understand, if you will, first of all, sort of the general set of players in a biological system. We've talked about the major categories of biological molecules. We have talked a little bit about enzymes and how they work, and we'll actually get more information about individual enzymes as we consider different metabolic pathways. But now we are actually going to, in effect, move inside the cell and try to understand some very well studied pathways in our body. We'll only be talking about limited pathways. And yet, hopefully, it will give you some sense of how the body transacts its different situations within the cell. We'll understand a little bit more about how enzymes work generally and specifically. We will begin to talk about regulation, which is very complicated and moves well beyond the organic chemistry aspects of these reactions. And we'll talk about, again, we'll probably have at least one more specialized topic where we will consider sort of the clinical implications of problems with certain metabolic pathways. All right. So glycolysis is a 10-step process that occurs in the cytosol of effectively all cells. All cells require energy, and the utilization of sugars, in particular glucose, is essential to the survival of most cells. There are some ways to work around this, but in the end, cells need a source of energy, and for most of our lives, glycolysis is going to provide molecules that will be used to generate high energy molecules. So 10 steps involving 10 different enzymes within the cytosol. The product of one of these steps then becomes the substrate of the next step, and so on and so forth. And one might ask, why so many steps? This is, why not just take glucose and fry it, burn it up, and let the energy out? Well, the answer is not fully understood, but part of it is that if one were to liberate all of the energy from a glucose molecule, it would actually be too much. It would overwhelm the cell. It would cause too great a shift in temperature and would result in the death of the cell. From a different point of view, some of the intermediates are actually used for other purposes. And so by breaking it down into multiple steps, we have access then to intermediates that can have chemical value for other processes. In addition, if we're going to release energy, we'd like to release it in smaller amounts that can be captured chemically. And the amount needed is the amount needed is the amount, well, the amount released has to sort of exceed or be equal to the amount that you will need for synthetic anabolic processes. We talked about this relationship. So, where the process then of glycolysis are stuck. Hello? All right. call. Okay, I'll try to be very careful with the microphone. So, very briefly, these 10 steps are coordinated in such a way that the product of one becomes the substrate of the next. 7 of the 10 steps are reversible. 3 of them are irreversible steps. And it turns out that those are the steps that are regulated. So anytime we come up to a situation where the pathway becomes, you can't go back, there is a level of regulation. By far and away, the most regulated step in glycolysis is step number 3. So just keep track of that. To begin with, steps 1 and 3 are going to require the use of ATP, this high energy molecule that we had talked about, to bring about a favorable coupled reaction. And these 2 steps are irreversible because there is a really substantial energy drop as we go through each of those 2 steps. Step 10 is the other irreversible step. I'm going to go through these steps as best I can. By showing you the actual reaction mechanism, and I'm going to do that on the board. So let me just introduce you to these steps. So hexokinase is the first of these. It is a step in which we phosphorylate glucose on the 6th carbon. Step number 2 is a isomerase reaction where we convert our glucose 6-phosphate into fructose 6-phosphate. This requires only the movement or the repositioning of the carbonyl from carbon 1 to carbon 2. Step 3 is another kinase reaction in which we add now a second phosphate. So this uses a copy of ATP as the source of the phosphate. This too is irreversible, and this is considered to be the first committed step of glycolysis. That is to say, once you've gone through this step, you are going to produce pyruvate, which is the end product of glycolysis. The 4th step is a step in which we cleave our 6 carbon sugar into 2 3-carbon pieces. So aldolase is able to generate a dihydroxyacetone phosphate and a copy of glyceraldehyde 3-phosphate. I am going to now drop the slides and take my chances on the board. I apologize that we're having trouble with the mic. Actually, the whole sound system, the podium mic doesn't work as well. So assuming that this is going to die soon, I am going to outline the step-by-step process in which we convert glucose into glucose 6-phosphate. Then I'll talk about the isomerase. The phosphofructokinase actually follows this very closely, except that I'm going to involve a different hydroxyl group in the phosphorylation event. And then step 4, the aldolase, which is this step in which we cleave our 6-carbon sugar into 2 3-carbon pieces. So I'm actually going to set this microphone down because I can't hold this like this. I could put it back on me, but I have a feeling it's going to die pretty soon. Anyway, I'll try it. All right, so we begin with ATP. I've shown this as ADP with an additional phosphate on it. So, and we have the glucose as shown here. I've left off a hydroxyl group. There is a base, unspecified, unknown really at this point, on the enzyme. So this is part of the enzyme that's going to activate this hydroxyl group. In effect, it's doing something similar to our catalytic triad that we saw before. It is, in effect, going to abstract this proton, and this pair of electrons now is going to attack the phosphate of the terminal it's going to attack the phosphorus of the terminal phosphate of our ATP. This leads to a breaking of a bond, and we're left with ADP minus, which is typical. But we've now coupled the phosphate to the 6 carbon hydroxyl oxygen. So we now have glucose 6-phosphate. Okay? So it's a relatively simple process. The enzyme itself is very interesting. It exists as a dimer. It has a large it looks a little bit like a pizza pie with a piece missing. And the substrate binding sites are right at the very apex of that opening. As they bind, and both of them will bind before this happens, as they bind, the enzyme will envelop them. This is not uncommon, but the enzyme will actually surround these two and place them right adjacent to one another, which then initiates the reaction. Once they have formed glucose 6-phosphate and ADP, the enzyme reopens, they diffuse out of that space. Okay, moving on. Let me note that there are animations of these that were prepared by Dr. Wood with the help of students that are on Learning Suite, and they are actually very good. I will mention that they provide more detail than found in the book, and they also provide, or they also choose one particular proposed mechanism. There are, it turns out, many possibilities for which group on the enzyme is conducting certain types of activities. All right, let's bring in then our glucose 6-phosphate. Okay, so over here now, attached to this, we have this, we have this arrangement here. So the first thing that happens as part of the hexophosphate isomerase reaction, so this is step 2, is that I'm going to open the ring. This is facilitated now by a base, and it is proposed, I think, by some to be a lysine. So the lysine is part of the active side of the enzyme. And there's going to be a pair of electrons abstract a proton here. This is going to bring about the reformation of the aldehyde. Remember, that's where we started. This pair of electrons swings out, and there is a base, again, part of the enzyme active site that is going to contribute a proton. All right. Let me redraw this with these changes in place. So we've reformed the aldehyde, and we pick up the proton from the side group here. Will look as follows. Okay. Now this is where the reaction gets interesting. It turns out that there is another base, and again, this is not absolutely known. And again, it is proposed that a second lysine in the vicinity of the active site is going to abstract this proton right here. And this pair of electrons there then is going to form a double bond here. It's not bond very well. So this pair of electrons moves here, and this one moves out here. And I think, according to at least the one proposed mechanism, there is a glutamic acid that is going to now contribute a proton to this pair of electrons. I know I'm going through this pretty fast, but all of this is captured on those animation videos that are part of the slides, and they're also listed separately in Learning Suite. So let me redraw this now with the double bond between the two oxygens. I have now this with the hydrogen present. And okay, that's where we are. This interesting intermediate, you'll notice, is at least symmetric around this double bond. This is called an ene, double bond, diol intermediate, sometimes called an ene diolate. But what you see is then that I could, if I take off either of these protons, I'll reform the carbonyl. If I take it off here, I form the aldehyde, glucose. But if I take it off here, I now have the carbonyl on the 2-carbon, and I actually have fructose. And so that is the proposed mechanism, is that there is a base, again, unspecified, that removes this proton. I now form a double bond here, and this pair of electrons comes out, and we will have it pick up a proton from one of the protonated lysines in the vicinity. I don't know if it's this one or that one. I'm not sure that anybody knows, but that is what happens. Okay, so let me now redraw this with the carbonyl on the 2-carbon. We have this picking up a proton. I left the proton off, but we now have we have this species, CH2OH. And at this point, this base will re-abstract this. This will attack then, this pair of electrons will attack this. And we will close the ring. And we will produce, and this will push out, pick up this proton, and we'll now end up with fructose cyclized with its 6 phospho species. Okay. Step 3, the phosphofructokinase 1 reaction. So let me draw this a little bit differently here. Just so you can see. I'm going to have this is our CH2OH here. Oops. We have our fructose, and at this point, there is a second phosphorylation event that's going to take place involving this 1 hydroxyl group. We're going to use this other enzyme, phosphofructokinase 1. It exists as a dimer of dimer. I forgot to mention that the hexose phosphate isomerase uses a barrel. It actually has a barrel for an active site. It also occurs as a dimer. The phosphofructokinase 1 involves a dimer of dimers, that is 4 copies of the same enzyme that are going to be present. Okay, the phosphofructokinase 1 is going to perform it's going to carry out a step very similar to the one we saw for hexokinase. We're going to be something, there's going to be a feature of the active site, a base, that will abstract this proton. This pair of electrons then will attack the phosphorus of the terminal phosphate group, attaching it to the 1 carbon oxygen. So we replace the hydrogen now with phosphate, and we end up with fructose 1,6-bisphosphate. This strategy allows both 3 carbon pieces that are produced by the aldolase, step 4, to be phosphorylated. And it turns out that all of the intermediates from glucose through pyruvate, all of the intermediate steps have phosphorylated intermediates. The strategy here is to keep things from moving through cell membranes, organelle membranes, or out through transporters back out into the circulation. So once the glucose is inside the cell, it's rapidly phosphorylated. That keeps it in place. All of these phosphates prevent materials present in the cytosol from moving into other organelles. Okay. Let me move on then to aldolase. Aldolase has an alpha-beta barrel. It exists as a dimer. And we are going to, it has the ability to open up our fructose 1,6-bisphosphate. So I'm going to draw that out here. Oops, it's a carbon. And okay, so this is our fructose 1,6-bisphosphate produced in step 3 of glycolysis, the phosphofructokinase step. The enzyme that's going to bind this and act on this is called aldolase. And the idea is we're going to cleave this into 2 3-carbon pieces. This enzyme, even though it's a reversible reaction, it has the ability to form and break this bond between the 3rd and 4th carbon quite readily, depending on substrate product concentration. This enzyme has a lysine with a free amine, and this is going to undergo what's called it's going to form a Schiff's base. It's going to undergo a condensation. This pair of electrons is going to find this carbonyl carbon attractive. Down here, there is a base. We'll see other features as we go along. So this pair of electrons then comes in and binds. This is going to push a pair of electrons out here, and it is going to, I think Dr. Wood's presentation shows this as this proton coming from solution. I've seen other depictions where the proton comes from a base, a protonated base near the active site. Suffice it to say that we now form a hydroxide out here temporarily. Okay. And the following then reaction takes place. This is going to remove a proton. This pair of electrons is going to move here, and this is going to come off and pick up a proton from, I think this is glutamate, but I'm not absolutely sure. Okay, so this base that's part of this side of the enzyme is going to remove a hydrogen here, leaving us this. This is going to form then a double bond to this carbon. This is an imine. This pair of electrons will, this hydroxyl will come off, pick up a proton and become water, and we're left with this negatively charged species. Okay, this is just binding the substrate. This reaction is a spontaneous kind of reaction, but now the work begins. So down here, and this is argued about, is either an aspartate or a glutamate with its hydroxyl group out here, carboxyl group out here. It is going to take off this proton. We're going to form a carbonyl. This pair of electrons is going to shift up here, and this is going to move electrons here. Okay, I hear the bell, so we're just out of time. Let me see if I can just show you now that we are cleaving this piece. We're forming this double bond. We move this pair of electrons here. At this point, there's nothing holding this half of the molecule, and this comes out. This is the first of these products. This is glyceraldehyde 3-phosphate, and it comes out of the pocket. All right. These electrons now come back to form the double bond. This pair of electrons comes out and picks up this to generate this species here. We have this double bond here. And we now reverse the formation of the imine. This water comes in and hydrolyzes this bond. It comes off as C double bond O. So we reform the carbonyl that was present in fructose again, but now we have just a 3-carbon species. This is dihydroxyacetone phosphate. It is the second product of the aldolase reaction. Again, this is described in more detail in the slides. The animation is embedded in the slides, but the animations are also present as a series of animations within the content of chapter 14. And they are prepared by Dr. Wood. I am sorry about the problems with the sound system. And thank you for your patience. And we will call it good for today. Thanks.